The last example had us calculate the pH of a weak acid and kind of walked us through step by step, and I honestly don't usually do that. Here's how quick and easy it is to calculate the pH of a weak acid. Number one, you need the equation because we're going to set up an ice table. So we're going to start with some hypochlorous acid, HClO. We'll put the water in there. There will be a hydrogen transfer between the acid and the water. We'll be left with the ClO minus ion and H3O plus hydronium. We're going to set up an ice table. ICE. We'll start with the initial concentration of the acid, 0.1 molar. We don't care about the water because it's a pure liquid. The products will start at 0. We know it shifts forward, so we're going to go down by X. We don't care about the water. Up by X, up by X. So at equilibrium, we got 0.1 minus X, X, and X. You will be given the K value. Ka is 3.5 times 10 to the, -8. That's small. That equals X to the first times X to the first all over 0.1 minus X to the first. Now, a lot of times people will get so good at these that right away they'll plug this in as X squared. Like, well, I know it's X squared. It's X times X on the product side. All right. Since that K value is small, let's 5% rule this thing. That saves us from having to solve this quadratically, which, I don't know, maybe that's fun to you. I've got better things to do. This really makes your math a lot quicker. So we'll cross multiply 0.1 times 3.5 times 10 to the -8, which is just 3.5 times 10 to the -9 equals X squared. We'll take the square root of both sides, square root, and boom, here's X. Square root 3.5 times 10 to the -9. Holy moly. Even X is super small. 5.92 times 10 to the -5. Okay, do you think the 5% rule is valid? That X is crazy small. I mean, I knew that X was probably going to be small. We're not going to dissociate by much if the K value is so small. Do you think that I'm going to waste my time checking the 5% rule? Heck no! I'll say I did, though. 5% rule. Check. I thought about it. Qualitatively. I checked the 5% rule. There's no way those numbers differ by more than 5%. I mean, 0.1 is small to start with, but we're only shifting forward by like 5 times 10 to the -5. That's crazy, crazy tiny. Okay, so now that I have X, the only particle that I really care about, which I suppose I could put this in again as a scratch, we never used the water. I care about X being the hydronium concentration. So if I want pH, here we go. pH is opposite log of X. 5.92 times 10 to the -5. That's the concentration of H3O hydronium. We plug that in, and I get the original molarity had 3 sig figs, so maybe I'll leave 3. How about a pH of about 4.23? Done. These weak acids are really not that bad. They're very similar. All of them are very similar. You'll take your original molarity, your products are 0. You shift it forward, and it's almost always a 1-to-1 ratio. which really makes your math simple then, because when you have your ACE table, often you'll have something that looks very similar to this. X squared on top, the original concentration minus X on the bottom. For weak acids, the K values are small, so you can always use the 5% rule. Once you get X, plug it in, opposite log. X is the concentration of the hydrogen ion. There's maybe a couple extra steps in comparison to a strong acid, but weak acids will all be set up the exact same way.